we have been discussing the Bayer's process for production of pure alumina, and I mentioned that this alumina finds many applications in medicine, in cosmetics, as a grinding reagent, many others, but its main use is in aluminum electrolytic cell for aluminum production. Now, let us see how a cell looks like. Here I show schematically an electrolytic cell. Now, you will find an electrolytic cell. This is the electrolyte which has Al2O3 dissolved in cryolite. Alumina is continuously charged here, and there is a frozen crust of electrolyte which is all around, and this floats on top of aluminum that is continuously produced. Anodes are two graphite blocks. There can be many, but I have shown two graphite blocks. These are anode bars which are supplying current. Two graphites anodes dipped into cryolite which has alumina in solution. Aluminum that is produced goes to a graphite cathode. The whole thing lining is the cathode. Aluminum is attracted here, deposited here. This is the basic scheme of now gases that are produced will bubble out, and there are ways and means of collecting them that I will show you later. Basically, it is a steel cell, and you will have the ore insulation. There is an insulation at the bottom. On top, this is the cathode lining, aluminum. Then you have the electrolyte. Then you have the solid crust. Now, it is a very tricky situation. Now, let me read out what is there on top. This is the electrolytic cell for electrolysis of aluminum. The cell is sunk into the floor with the top portion about 0.3 millimeter above the ground level. It essentially consists of rectangular refractory lined steel boxes, each around 5 meter long, 2 meter wide, 1 meter deep. They are not very deep. Remember, I have always said that electrodes you cannot go for depth, and the cathode lining, which consists of refractory bricks, is faced with carbon mixed with a tar binder. Sorry, there is a correction here. There is no question of a cathode which is hanging vertically. Here the cathode is a horizontal cathode. Sorry, and the cathode area is the horizontal cathode area, and the cathode lining, which consists of refractory brick, is faced with carbon mixed with tar binder. So, this is the basic scheme. Now, it is a very tricky situation which I try to explain to you. We have cryolite, which is a natural mineral at 1000 degrees. When it is molten, its density is just 2.1. Aluminum which is produced is slightly heavier than that. So, it sinks to the bottom. Alumina which does not dissolve or which you do not want to dissolve will form a solid crust, will float, because its density is his density is 3.96. Okay. So, it is there as a solid crust. Now, the real trick is here, that the density of cryolite will go up if more and more alumina go into that, because it is of higher density. So, if you dissolve more and more alumina, its density will go up. We do not want the density to become too high, then aluminum will not sink so effectively. Fortunately, we cannot dissolve too much of alumina anyway, because there is a limit. We can at 1000 degrees we can dissolve only up to 15% alumina, but still nobody would like to go to that. We would like to maintain a density difference. So, one would operate at about 8% alumina only, not more than that. So, this is the situation. Temperature will be 980 to 1000 degrees centigrade, say 5, 6, 8% alumina, and then we have a separation between cryolite and aluminum. Aluminum stays at the bottom above the cathode, graphite cathode. It is also protected from everywhere, so that there is no question of its getting oxidized. This is the basic scheme. Now, there are many requirements that we have to keep in mind in this electrolytic process. We want lower liquid temperature, means we have to operate at as low a temperature as possible, because then we will get a higher current efficiency. Otherwise, we will be using current to generate heat. We have to decrease solubility of the metal in the fused salts. Please remember, I had given some lectures that many metals dissolve in their own salts, and if you do that, then it is a metal loss. That can be decreased by adding other salts. If you recall that, if you add third, fourth, fifth salts, then the solubility of the metal in its old salt goes down. Increase, if possible, solubility of alumina, not decrease. We do not want to decrease alumina solubility beyond 2%. There is a minimum limit, and I will discuss why. We have to increase electrical conductivity. There are many requirements. We have to decrease density for better separation of metal and salt. Now, if we increase alumina concentration, then you need less voltage for decomposition, but increasing alumina concentration in cryolite will mean increasing the density, bringing it too close to aluminum for good salt metal separation. So, these are contradictory requirements. We do not want too high an alumina concentration, because then the density will go up. So, we want to decrease density for better separation of metal and salt. We have to decrease vapor pressure and metal loss. We do not want vapor pressure to be high. It must not produce the whatever is being electrolyzed any ionic species with discharge potential lower than cation or anion, all kinds of problems, requirements. Before I go deeper into it, just let me give you an idea about where energy is going in aluminum industry. I have been mentioning that it is very energy intensive. 2% of energy in bauxite processing, caustic soda processing 4%, alumina production about 20%, because it needs grinding, autoclaving, all kinds of pumping, this, that, it will require some. Anode preparation, we have to make graphite anodes, but maximum 75% is going into primary smelting, means the electrolytic process. That is where maximum energy is consumed. Now, I have all along been saying that essentially you are adding alumina to make a solution of alumina in cryolite, which is Na3AlF6 or 3NF.AlF3. But in fact, many other compounds have to be added in some minor amounts. Here are some of the things with which people have experimented for years. Why we require smaller amounts of these things? Let us consider that. Solvent cryolite needs some additives to suitably modify solvent properties, because there are many requirements of the electrolytic processes. And here we are giving some qualitative effects of various additives to cryolites. What happens when these are added? Now, this means that causes increase, a downward arrow means causes decrease. This means that effect is non-linear and this means highly non-linear. Some of them you should easily understand, some you cannot understand, they have been found by trial and error. If you increase Al2O3 this is Al2O3 solubility. Please remember this word is Al2O3 solubility. Now, if you add calcium fluoride, this solubility will increase, aluminum will decrease, this will decrease it, LiB will decrease it. All salts if you add will decrease Al2O3 solubility because they are also going into cryolite. Sodium fluoride we do not know. If you increase temperature, solubility will increase. So, while it may be necessary to add other solutes for various reasons that we will see, all these will decrease solubility of Al2O3 that you want to dissolve in the solute. What will happen to electrical conductivity? Calcium fluoride will decrease it, aluminum fluoride will decrease, lithium fluoride will decrease that, magnesium fluoride will decrease. All of them will decrease electrical conductivity. Some will increase density, some will decrease density. You can easily say that if you add something like sodium fluoride, which is a very light molecule, then it will decrease, but some others will increase. Viscosity is also important, because on viscosity will depend separation of metal and salt, how metal will go through and trickle through, how they will be handled. Some increase it, some decrease it. More important is what is the effect on melting point. Now, all these additions excepting sodium fluoride is good from the point of view of melting point, because melting point decreasing is to our advantage. Metal solubility, any foreign ions will decrease metal solubility. So, many of them metal solubility will decrease, surface tension effect, vapor pressure effects are also complicated. So, people play around with all these additives in the industry, and different industries have developed their own formulas as to what to add, what not to add. Two are very common. One, must add some calcium fluoride, some aluminum fluoride. These are the most common things, and what they do we will see later on. Now, all these additives are to achieve this criteria: lower liquid temperature, decrease solubility of metal, increase if possible solubility of Al2O3, increase electrical conductivity, etc., 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 etc. And this has to be achieved in this cell. Now, the effects of various parameters of current efficiency or energy efficiency have been determined in the industry by a lot of R&D work. Many researchers have worked. Here is an equation that I am giving. I am again taking out from a book, and this book you must see, the 3 books I referred to in the morning, you must see at least for aluminum, discussions on aluminum, that current efficiency is given empirically by an equation written here. There is a negative term with respect to concentration of alumina, but here is a term alumina concentration square. Current efficiency will increase with aluminum fluoride addition, both are plus. Current efficiency increase with calcium fluoride addition. current efficiency will decrease with temperature obviously, and there are some dimensional things also like inter-electrode separation. If the inter-electrode separation, if it increases, this term will increase, therefore, current efficiency will drop. So, the distance between the cathode and anode, both graphites, they have to be minimized. See here, they have to be minimized, because if this increases, this term will decrease, current efficiency will decrease. If this is decreased, this will increase, this will increase. So, the two electrodes must come close together, but then there has to be some distance also, otherwise how will you, the resistance of the electrolyte has to provide heat. So, there is a kind of compromise they have to work out, different industry do it differently. And in many cases they can even go to a distance of only about 0.5 centimeter between the one electrode anode and the cathode. So, there are thin layers of cryolite and metal. Now, what are the key changes in modern operations, say compared to what happened in say 100 years ago? First of all, they have now found out cells where there will be continuous feeding of alumina to cell, continuous feeding of alumina, continuous removal of aluminum, higher excess of aluminum fluoride, a lot of aluminum fluoride excess is being added, lot of calcium fluoride excess 5% is being added. Current efficiency in the beginning was 7%, has gone up to some 96% today, means only 4% of the current is going into reactions that we do not want. 96% is going into decomposition of alumina to aluminum. Energy requirement is coming to gradually a limiting value of 13 kilowatt hour per ton, almost coming to the practical minimum. These two dots are wrong, this should not be there. The theoretical minimum is even less, it is about 6. Why theoretical minimum? Only the power required to dissociate aluminum, but we need some energy also to keep the electrolyte hot. So, the practical minimum is above theoretical minimum, but in the last 20 years or so, industries are almost able to bring it to the practical minimum. I will give you some figures to this effect little later. Now, let us make some calculations about decomposition potential, and for that I would request you to read up something that I have given in this book on introduction to molten salts, slags and glasses, and also extraction of non-ferrous metals, how you make some simple calculations to find out what is the theoretical requirement for voltage to dissociate. Now, for that you know a fundamental formula. If you want the free energy of formation, say delta G, then it can be equated to minus Z F Faraday and decomposition potential E. Delta G is equal to minus Z F E. Put the value of Z, which is valency for aluminum, F Faraday constant, you get the decomposition potential in volts. So, there is a correlation between free energy of formation in calories and decomposition potential in volts. Now, when you have Al2O3 in cryolite, and you are applying voltage to decompose Al2O3, you are not decomposing pure alumina, you are decomposing alumina in solution. So, you have to find out the decomposition voltage required for alumina in solution in cryolite. How do you find that? That calculation is given here I have lifted it from one of my books, and that is why I left the equation numbers here also, because it will be easier for me to refer to them. Sorry, it is a long write up, but let me explain what it says. It is not so difficult. Before discussing the technical aspects of Hall-Héroult process, I am saying it would be appropriate to first estimate the voltage required for the process of dissociation. The theoretical computations given here are according to somebody I have given the reference. Now, for a cathode of aluminum and an aluminum anode of oxygen, let us consider an ideal situation. This does not happen, that you have alumina in cryolite, you have an electrode where aluminum is being deposited, another electrode where oxygen is deposited to produce oxygen ion to oxygen. For that you need a platinum. That is not how it happens in the industry. But let us say in the lab we find out the theoretical voltage required when Al2O3 is decomposed into aluminum and oxygen. So, we need a platinum electrode. Now, this is how we calculate. We want to know the decomposition of alumina into aluminum and oxygen, and this alumina is in solution. It is 0.5 Al2O3, aluminum 0.75 O2. I am writing it in this form, so that we are always getting one atom of aluminum. Suppose the free energy change for this is delta G1. The reaction may be split into a series of reactions, and this you must understand. Firstly, there is considered pure alumina. The formation reaction is 1 aluminum, 0.75 oxygen, Al2O3, C means solid. Now, this solid alumina, assume that it is becoming liquid alumina, and that liquid alumina is dissolving in liquid cryolite to produce this alumina in solution in cryolite. This is a very tricky way of doing things. Now, suppose you are mixing sugar in water. Now, in the sugar solution, sugar is not there as solid, it is in a liquid state. So, we can visualize this reaction as solid sugar first melting to make liquid sugar, then liquid sugar plus liquid water giving you a liquid solution of sugar in water. So, in the process of dissolution, somewhere sugar is melting. As well, that is how you can also understand why when many salts, when they dissolve in water, the water becomes cooler. If you take silver nitrate, dissolve it in water, you will find the temperature drops. Why? Because the solid silver nitrate has melted notionally, and for melting it has extracted heat from water, and then it has the two liquids are mixed, so the water has become. So, they say when you have sarbat in summer, it cools you. It is true, because the moment you have put some sugar in water, sugar has extracted heat from water to melt, liquid sugar has dissolved now with water, and you have got a cooler water. You can actually see it by using a thermometer. Something like this is happening here. You have alumina solid, we visualize it as becoming liquid alumina. The liquid alumina is reacting with cryolite to become a solution. So, we have split the reaction into three. Firstly, the formation reaction, then the state change reaction, then dissolution. We will find these values, then add them up to get this value. Now, at 1000 degrees for the reaction aluminum plus O2, Al2O3, the C again is solid. We get from our Ellingham diagrams the free energy change there is given per hydrogen molecule. So, you have to recalculate it here for 0.57 I have to take, that is given as minus 207 kilocalories. So, delta G2 is this. We can calculate delta G3, means solid going to liquid from the heat of fusion of alumina. Here delta G3 is equivalent to converting 0.15 L2O3 at 1000 degrees to the molten state, and from standard tables you obtain it at 3800 kilocalories. Delta G4 corresponds to dissolution of L2O3 molten at 1000 degrees into cryolite. For 1 mole of L2O3 we have delta G4 is RT ln activity of L2O3, because this will depend on activity of L2O3. L2O3 is the activity of alumina in cryolite. Temperature is this, R is this. If it is assumed that the bath contains 8% alumina and the rest cryolite, then the mole fraction of alumina works out to be 0.15. If you take the molecular weight, mole fraction is 0.15. Assuming that the solution is ideal and also the activity of alumina is equal to its mole fraction, we get delta G4 is equal to RT ln this by 2 this. So, now you add up all this to get the final value, and that is equal to Faraday constant Z, which is 3 valency into E. This E will give us the decomposition potential, and by doing this calculation, decomposition potential theoretical for a solute containing 8% alumina comes out to be 2.22 volts. This theoretically calculated value compares with experimentally obtained values between aluminum and platinum oxygen electrodes, which lie in the range 2.1 to 2.15. So, theoretically we have calculated a value which is very similar to what actually can be experimentally obtained in a lab using platinum electrode and aluminum electrode. Now, there is a little bit of error in this calculation, because we are assuming that when the mole fraction for 8% aluminum is 0.15, we are taking the activity is equal to 0.15. Actually, this is not quite so. You go back to my discussions on Temkin model for fused salts. If we consider L2O3 in 3NaF into AlF3, that is Na3AlF6. This is giving us 2 aluminum ions and 3 oxygen ions. This is giving us 3 sodium ions, 1 AlF6 3 minus ions. So, ideally these are the species in the melt. Now, assume, to make it simple, that we have 10 mole percent Al2O3. The earlier calculation was for 15 mole percent, but let us say 10 mole percent, means for 1 molecule of Al2O3, you have 10 molecules of cryolite. Now, what is, according to Temkin's equation, activity of Al2O3? It will be ionic fraction of aluminum 3 plus ions square into ionic fraction of oxygen cube. Now, remember what I had said about Temkin's equation. I had said that Temkin proposes that in an ionic melt, you have two sublattices, one lattice for cations, one lattice for anions. They are mixed together, intermixed. Cations can move in the cation sublattice, anions move in the anion sublattice, such that a cation is always surrounded by anions and anion is always surrounded by cations. When we say activity of alumina, we really mean the probability of finding two aluminum atoms in close proximity of 3 oxygen atoms. Two aluminum atoms in close proximity of 3 oxygen atoms. Now, the probability of finding two aluminum ions will have to be calculated with reference to only the cation sublattice. Probability of finding oxygen anions, 3 of them in nearby areas, will be in reference to only the anion sublattice. And because we are calculating probability, we are talking about 2 aluminum. So, it will be ionic fraction of aluminum to the power square, and this will be ionic fraction of oxygen to the power cube. What will it be? Instead, we can write it like this: moles of aluminum ions divided by all cations, aluminum cation, all cations to the power square. This will be moles of oxygen anions divided by all anions to the power cube. If we are considering 1 alumina and 9 this, we are going to get out of 1 2 aluminum. 2 aluminum is there, and there is how many more cations will come there? It will be 2 plus 10. So, we have 1 L2O3 and 9 Na3AlF6. So, 9 into 3, 27 sodium cations are there, square. Oxygen is 3, 3 plus, there are in 9, you have 9 of these, 3 plus 9, and this is cube. Assume this is almost 30, so it becomes 1 by 15 approximately, and is 1 by 4 square cube. This is very, very small. It is very small. So, there we had said that for an ideal solution 15 mole percent means 0.15, therefore, activity is 0.15. That is not true. According to Temkin's equation, this assumption is not valid, that we say that 8% aluminum and rest chloride works out to be 0.15, means 15 mole percent, mole fraction is 0.15. So, we said if the solution is ideal, reactivity of aluminum is equal to mole fraction 0.15, it is not true. This actually should be practically very small, it cannot be 0.15. According to Temkin equation would be almost near 0, which means it will be much smaller. If it is much smaller, then this value that you are calculating will be smaller still, and perhaps it will be much closer to this what you are finding experimentally. Whatever it is, I am just going into the finer thing, because I want to relate something I am doing now to something we have done earlier, just to show you the interesting aspect of Temkin's equation. But what it tells us now, we can calculate theoretically, and it find that if you had platinum electrodes, then you would need about say 2.1 to 2.15, which means little more than 2 volts. But in reality, we need less than 2 volts. Why? It is because we are modifying the anode reaction. Cathode reaction is remaining the same. Aluminum ions coming to the aluminum electrode getting discharged, but we do not have platinum for discharge of oxygen. Oxygen is now getting discharged on graphite, but graphite is not a neutral electrode, it is a consumable electrode. That oxygen ions, when it reacts, deposits on carbon, it consumes oxygen, carbon to produce CO or CO2 depending on the temperature. And because oxygen is consumed, the decomposition reaction is aided, made simpler. Let us calculate that. We say that in practice a consumable graphite electrode serves as the anode. Therefore, we have to calculate the decomposition potential for an aluminum liquid cathode and a carbon, this crystalline solid anode. To do so, this reaction 6.15 that I had shown earlier has to be combined with carbon oxidation reactions, 0.75 O2, 0.75 carbon giving you CO2, similarly oxygen reacting to carbon CO, which means now we will get 2 more values of delta G 5, delta G 6, which are these values. These will have to combine with the reaction I had written earlier, and then we get this is the final reaction. Alumina in solution in cryolite reacting with carbon in the anode produces aluminum metal and CO2, or alumina in solution reacts with carbon in the anode produces aluminum metal and CO. Whether it will be CO or CO2 will depend on temperature. You know, the higher the temperature, more the CO, lower the temperature, more the CO2. For this, our decomposition potential would be 1.19 volt, which means carbon coming into the picture, eating away oxygen, has made the decomposition easier. Had it been only aluminum and oxygen, there was certain voltage, but this oxygen is now consumed by carbon. So, the dissociation is made easier. So, the voltage is almost made half. If it is forming CO, which is more likely because you are operating at 1000 degrees where there is more CO than CO2, it is even lower 1.05. This is a big advantage of a consumable carbon electrode, but there is a disadvantage. You are not producing life giving oxygen, you are producing life threatening carbon monoxide and carbon dioxide. This is a fact in the industry. You had an advantage on one side, you are consuming less energy by using less voltage. Less energy means somewhere you are producing less CO2 in the power station, but here you are producing more CO2. What to do? Unfortunately, there is no other way of doing it. People have thought of getting rid of this carbon, and lot of work has been done, and almost successful has been what we call an anode, which is not consumable, inert, not platinum. If we had tons of platinum for the industry, it will be a beautiful process. You will need little more voltage, but you will produce oxygen. There is always use for oxygen. People are using is titanium dioxide inert anode. People have tried this. It has still not become industrially successful. If that is there, you will not use carbon for anode or cathode, whatever, and we will produce oxygen and we will have an inert electrode. But there the voltage will again go back to the more than 2. Okay. Now, so what we have today is this process where you have graphite anode and a graphite bottom layer as cathode. Now, so from the foregoing discussion, it is evident that graphite aids the decomposition of Al2O3 because it reacts with oxygen to form CO and CO2. Under normal operating conditions, about 50% by volume of CO is produced. The percentage may increase considerably at low current density. It depends on current density also. In general, we assume the value is calculated from reaction this and this. We take an average. So, theoretical decomposition voltage using graphite electrodes comes to 1.125. Now, somebody had another interesting idea. They said that if we can consume that oxygen by a consumable graphite, then we are bringing down the voltage, but two problems are coming. You are using CO and CO2 plus you are consuming carbon, means you have to continuously recharge that anode, and that is a problem in the industry I will come to. Actually, what happens is the anode is continuously consumed. So, either you keep on changing it from time to time from the top, this is what is done. Electrolysis is stopped, a small amount left is removed, a new anode is screwed again and the process started, or do we have a continuous anode called Soderberg electrode, that a carbon paste is pushed from the top, and as the paste keeps going down, it gets dried up and becomes the solid anode, which is consumable. So, it is getting consumed here at the bottom, but from the top it is being continuously fed. It is called Soderberg consumable anode. Some industries use Soderberg process, some use changeable anode. Whatever is, in either case you consume carbon, and that carbon should not be any carbon, it has to be special kind of graphite to be anode. It needs strength, it needs purity, it needs all kinds of things. Somebody has an idea that if the idea is to bring down the decomposition voltage by consuming the oxygen that is coming towards the anode, why can't we inject hydrogen near the anode? Let that oxygen ion react with hydrogen, just produce nice pure water. So, your product would be water, of course, as in the form of steam, and you will produce aluminum as metal, and your graphite will be protected also. You will lower the consumption of graphite, because bulk of the oxygen that is coming will react with this hydrogen. It is very good in theory. So, we can calculate that we have one reaction this, to that we will combine what happens if you bring in hydrogen. So, this will react with hydrogen producing aluminum. We can calculate its voltage will come to about 1.3 volts, which means it is not very much better than what we had for graphite. Its only advantage would be surely that it will lower the consumption of graphite, but it will not bring down the voltage. The other idea could be injection of methane, that you can calculate what will the decomposition potential if you allow the oxygen that is coming out to react with methane. So, overall reaction is this, you get hydrogen and CO2. This works out to 1.06 volts. So, there is not really advantage. First of all, technologically these may not be feasible. You cannot inject hydrogen at this high temperature into a cell, you can have an explosion. But it is interesting to look at the theory, but these could be the ways of lowering the consumption of graphite if you can inject methane or hydrogen, but nobody would like to try it out. It is good. So, the conclusion is the injection of hydrogen or methane would not be effective in appreciably reducing the decomposition potential of alumina. However, such an injection may effectively cut down graphite consumption and prove economical if hydrogen or methane is available at cheap rates and there is technology to use them the way it is being suggested. Same thing goes with natural gas. So, these are trials people try and try to see what to do, what not to do, but it does not work. Now, let me wind up today's thing by saying two other things. Aluminum electrolysis has a cell that is continuously being fed by alumina. It has to be continuously fed by graphite also for making an anode which is consumable. And the manufacturing process for carbon electrodes is a very elaborate thing. I have given a flow sheet that you take solid carbonaceous materials like petroleum coke, very pure, crush, calcine, grind, classify, blend with petroleum pitch, so that it can be given a shape. Then you get a carbon mass, you mold, you get green electrodes, they have to be baked, they have to go for inspection, then you have finished electrodes. Or in solder electrode is the paste which straight away poured into aluminum casing and is continuously fed into the cell, and it gets dried up as it gets lower down. So, that by the time the bottom comes in touch with the electrode, it has been baked. But look at all the elaborate processing that is required. You have to start with petroleum. So, it is not only an expensive raw material, it is also an energy consuming thing. You would have seen, I have given you some data that the whole process consumes some energy here. Somewhere I gave how much it will be required. Here, anode production, 2% of the energy of aluminum electrolysis is involved in that anode production because of all those problems. Then there is the question of cryolite. Now, cryolite is a synthetic mineral which is not available very widely. It will be available in places like Greenland and one or two other places. And you might think that once you have put in a cryolite, because it is only the solvent, alumina is coming, it is getting decomposed, cryolite stays as such, which is not true. Cryolite is not so innocent a solute. It also takes part in reaction. Small amounts of cryolite also decomposes, producing all kinds of things, which I will discuss next, which means you need a continuous supply of cryolite also. Although it is not really supposed to be consumed, it is only a supporting electrolyte for the solute, but you need cryolite. People have tried very hard to manufacture cryolite, where natural cryolite is not available. They have been successful also. Here is a flow sheet. Again, you do not have to remember the flow sheet, but I must tell you that cryolite can be manufactured. If you cannot simply add 3 molecules of sodium fluoride and 1 molecule of aluminum fluoride, say it is 3 NaF plus AlF3, it is now cryolite. No, we are writing cryolite like that, 3 NaF dot AlF3, to show it is notionally a combination of 2 minerals, but actual mineral is Na3AlF6. It is not a mechanical mixture of sodium fluoride and aluminum fluoride. So, it has to be manufactured specially. The process is like this. We will start with fluorspar, which is calcium fluoride, grinding, drying, batching, pulp, sulfuric acid treatment, decomposition, gypsum to waste, gas cleaning, adsorption, then hydrofluorosilicic acid and hydrofluoric acid treatment, desiliconization, decantation, hydrofluoric acid, etc., 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 whole lot of things. Finally, we will get cryolite. We will add sodium carbonate here somewhere to get this sodium part. The calcium fluoride part is coming from the top. So, you see it is a very complicated thing. Aluminum is coming from aluminum hydroxide. So, to produce synthesized cryolite, one needs a very elaborate setup, but some countries had to do it. Suppose they are in aluminum production and cryolite is not available in the market, natural cryolite, one has to manufacture. So, this is another research area. Okay. Now, I mentioned just now that cryolite, although it is a supporting electrolyte, is not sitting there doing nothing. Its main job is to be molten at about 980 degrees or so, dissolve alumina so that it can be electrolyzed. That is its main job. But unintentionally, it gets also involved in many decomposition reactions, and we get in the melt whole lot of ions which have come through reactions of alumina and the fluoride ions. These are some of the ions. Oxygen containing anions in alumina saturated melts. Oxygen has come from alumina because there is no oxygen in cryolite, but we do get Al2OF6 2 minus, this ion, that ion, that ion, and this depends on mole ratio of NaF AlF3. The mole ratio in cryolite is 3 NaF AlF3, means 3. So, if we are in this ratio, we will have about 0.1 of Al2O2 FH6 4 minus, we will have Al2O2 F4 2 minus about 0.2%. We will have a little bit of these two ions also. If you go below that, means if you add extra AlF3, then we get this ion. If you go more than that, means if you add extra NaF, then we tend to get more of these ions. Again, having the presence of these ions have some implications. We show here the proposed structure of some major oxyfluoro ions. These are unavoidable, but their proportion can be controlled by controlling mole ratio of NaF AlF3. Different industries operate differently. Some would like to go more on this side, some would like to go more this side, because they have developed their processes. I think I will stop here for now and take off from here in my next lecture and carry on. I would need another 2-3 lectures to talk about aluminum production in general. Then I would also devote some time to the aluminum production scene in India, and this will be one of the exceptions where I will discuss the Indian scene in particular. I will do that because for India aluminum is vitally important. It is an industry which sees expansion, which in the bid to expand is running into a lot of problems, because in Odisha there are huge deposits of bauxite and there are many companies which are coming forward for mining, and they have to now then occupy those areas. Many of these areas happen to be tribal areas where tribals have been living for many generations. They say they may not be agricultural land, they may be land lying, because in these aluminates and silicates and alumina silicates things may not grow, but the land belongs to them. So, they said what compensation do they get when these mines go. Actually, I will start with this, what some other countries have done about setting up such industries in areas where there have been people living for generations. Thank you very much. Okay.